When thousands of tons of steel and cargo meet heavy ocean swells, the ship's survival depends on a constant, invisible fight against gravity. Stability varies throughout a voyage, changing every time the crew loads or discharges cargo. Because the vessel's physical characteristics shift with its payload, the balance of forces must be recalculated for every crossing. Physics rely on two opposing points. Gravity pulls the ship's mass downward, while buoyancy pushes upward. When a wave tilts the ship, these vertical forces separate. Their horizontal distance creates torque, forcing the ship upright. This is the righting lever, or GZ. If this GZ distance ever shrinks to zero, the ship rolls over. Calculating the exact leverage available at any angle is the only way to predict and prevent a catastrophic capsize. To find that GZ distance, officers start with a standardized map provided by naval architects known as the cross curves of stability. This chart maps stability against displacement. Finding the ship's weight on the bottom axis, an officer traces up to the curves to find the righting lever. However, these curves rely on a theoretical baseline, the assumed center of gravity, seen here as 9 meters. In reality, iron ore sitting low in the hull, or containers stacked high on deck, will move the actual center of gravity away from this assumed baseline. Relying on the builder's chart without adjusting for the actual payload ignores the physical reality of the ship. If heavy cargo is loaded onto the upper deck, the ship's actual center of gravity shifts upward, moving above the architect's assumed baseline. This top-heavy distribution makes the vessel less stable. This baseline must be mathematically corrected to reflect the true cargo distribution. As the ship rolls, the actual righting lever working to pull it back is physically shorter than what the cross curves predicted. The assumed center of gravity, actual higher center, and vertical axis form a right triangle. The true righting lever is the assumed distance minus segment gx. Using trigonometry, the correction factor equals the upward gravity shift multiplied by the sine of the heel angle. When the payload pushes the center of gravity higher than the baseline, officers must subtract this trigonometric correction to find the true margin of survival. The relationship is reversed when loading dense cargo, like steel coils, deep within the ship's lower holds. This concentrates weight at the bottom, pulling the actual center of gravity below the assumed baseline and directly increasing the ship's overall stability. Notice the new center of gravity, G2, sitting below original G, making the true righting lever longer. Using the same trigonometric principles, the shift in gravity is multiplied by the sine of the heel angle, and this correction is added to the tabulated baseline GZ. Regardless of cargo height, the sine correction mathematically links the abstract hull baseline to the physical reality of the water. To understand a ship's full behavior, these corrected values must be calculated across the entire range of motion, not just a single angle. This table shows the output of these corrections for a 6,000-ton ship. It lists the exact righting lever at 10-degree intervals, from a vertical position all the way to 90 degrees. Plotting these points on a graph reveals a specific diagnostic profile. Connecting them creates the curve of statical stability, visualizing the forces fighting to keep the ship upright. The curve's height shows how restoring force grows, peaks, and declines as tilt increases. This curve represents the vessel's operational boundary, a complete map of its resistance to capsizing. Maritime officers analyze the specific geometry of this single curve to extract 5 life-or-death parameters. This chart identifies the first parameter, initial metacentric height, or GM. This marker shows initial stiffness, determining how it resists small rolls. The second parameter is maximum GZ. This crest is the absolute peak leverage the ship generates to push back against a roll. Third is the range of stability. This defines the total width of the graph, where the ship still possesses a positive ability to right itself. Past a certain degree of tilt, the physics invert, and the ship reaches a threshold where it can no longer save itself. The fourth and most critical parameter is the angle of vanishing stability, or AVS. It's the exact point where the righting curve crosses the zero line. Beyond the AVS, the righting lever becomes negative. Gravity now creates a capsizing moment, forcing the ship over. The final parameter is the moment of statical stability. This translates the linear GZ distance into actual rotational torque. To find this total twisting force, the crew multiplies the righting lever by the total weight of the ship's displacement. A ship's survival is not guaranteed by its steel hull, but by the application of geometric corrections that align the builder's baseline with the physical reality of the payload.